Bioinformatics Micromodules, Constructing a Suffix Tree in Superlinear Time. In this module, we talk about an intuitive but inefficient algorithm for constructing the suffix tree. We then introduce some ideas that may be useful for improving it, and the corresponding second algorithm, which is still inefficient. In the next module, we will introduce some additional ideas to turn this second algorithm into one that constructs a suffix tree in time linear with respect to the length of the sequence to be indexed. Let us start with an intuitive way of constructing the suffix tree, which is to first build the suffix tree by inserting each suffix into it one by one, and then compress the suffix tree by merging every single child with its parent. This was also how we described suffix tree in the last module, but this time we focus on analyzing the time and space complexities. As an illustration, suppose we want to build the suffix tree of our reference sequence $$. Let us insert each suffix of it one by one, starting with the longest one. This longest suffix is the whole sequence, and if we insert it into the trie, it will become this one. Similarly, we insert the second suffix into the trie, and it becomes this one. Now if we insert the third suffix into the trie, but this time one special thing is that the first two notes are common with the first suffix, and thus we do not need to create these notes again, but just reuse them. The remaining of the construction process is just the same. We insert the fourth suffix, the fifth suffix, and so on until all suffixes have been inserted. Finally, we get the whole suffix tree. Now we start compressing the suffix tree into the suffix tree. We do it by performing a depth-first traversal of the tree. And every time when we reach a node, if it has only one child, we merge it with its child. First, we start with the root node. Since it has multiple children, no merging needs to be done. Next, we move to the first child of the root. Again, it does not have exactly one child, and therefore no merging needs to be done. In the same way, we ignore this second child of the root, and then we reach this node that represents the fifth character of the sequence. This node has exactly one child, and so we need to merge it with that child. But instead of doing it right away, we can keep traversing down the single child nodes until reaching the end of this path, and then merge all the nodes together into a single node. In the same way, next, we find these two nodes that need to be merged, and we merge them. The remaining of the merging procedure can be done in the same way, and therefore we skip the steps and show the final tree directly, which is the one shown here. How much time and space does this intuitive way of construction take? For the part of inserting the suffixes, since each character is inserted one by one, and each insertion requires an amount of operations unrelated to the sequence length, the total time needed is proportional to their total length, which is order n squared for a sequence of length n. The space needed is clearly also order n squared. Then when we compress the suffix tree, we need to traverse the whole tree, and merging a node with its child takes constant time, and therefore the total time is order n squared. The space needed is the size of the original suffix tree, which is also order n squared. Therefore, the whole procedure involving both steps requires order n squared time and order n squared space. Let's make some observations about the intuitive construction method and try coming up with some ideas to improve the time and space complexities. Here we use double quotes to enclose the word improvements because what we are going to propose may not immediately reduce the time or space complexity, but ultimately These initial ideas will play crucial roles in an algorithm that requires only linear time and linear space. The first observation is that the same position could be repeatedly involved in multiple suffixes, and therefore it was inserted into the tree again and again. For example, the $ symbol was involved in every suffix of the sequence, and therefore it was inserted a total of n times into the suffix trie. If we instead insert these n $ symbols, one right after the other, it might be possible for us to find some ways to reduce the amount of computations needed. This is the first idea that we are going to implement. In other words, although we are still going to have n iterations of insertions, each time we no longer insert all the characters in the ith suffix of s, but rather we insert the ith position of s in every suffix that it is involved in. We will illustrate this idea using our example in a moment. Another idea is that instead of creating the whole suffix trie before compressing it to form the suffix tree, it is better to perform insertion and compression at the same time. This can at least reduce the space complexity. Let's see these two ideas in action. Again, we try to construct the suffix tree of our reference sequence S, which is $. This sequence has 11 characters, and therefore we are going to have 11 iterations in total, each time inserting information about one position of the sequence. The first iteration is about inserting information about the first position of the sequence, which is this T highlighted in red. Based on our second idea, we insert the position information of it into the tree, which means creating this new node labeled with 1 to 1. Notice that we also show the actual character T here for reference, but the actual tree should not store it, and therefore we are showing it in gray. We also want to assign a type to each insertion, and this first insertion is referred to as type A, which involves creating a new leaf node. Next, we start the second iteration, and in this iteration, we need to insert the information about this A in its involvements of both the first suffix and the second suffix of S. First, we consider its involvement in the first suffix, which is the A highlighted in red here, in the suffix that starts with TA. Since there is already a child of the root for T, we do not need to create a new node, but only update the ending position of its label. We call this type of insertion type B, which only requires increasing the ending position of a leaf node label by 1. We then move on to the involvement of the A in the second suffix of S. This time, the root does not have a child node with a label starting with A, and therefore we need to create it. This insertion is of type A, just like the insertion of the T in iteration 1. Now for this T at the third position, regarding its involvement in the first suffix, since TA is already in the tree, we only need to update the ending position of that leaf node label, and thus this insertion is of type B. Similarly, for the involvement of this T in the second suffix, the ending position of the left child of the root is updated, and therefore this insertion is also of type B. Now we see a special case. For the involvement of this T in the third suffix, if we try inserting it into the tree, we notice that the right child of the root already has a label that starts with T. Therefore, we do not need to do anything, and this is called type C insertion. With this example, we have seen all three possible types of insertions. For the remaining insertions, we can go a bit faster. For the A at the fourth position of S, its involvement in the first and second suffixes lead to type B insertions, while its involvements in the third and fourth suffixes lead to type C insertions. Then for the C at position 5 of S, the 5 insertions are of types B, B, A, and A respectively. You can verify them by yourself. Then for the A at position 6, we have 5 type B insertions and then a type C insertion. For the T at position 7, we have 5 type B insertions and then 2 type C insertions. And so on. These are the results for the T at position 8. These are the results for the A at position 9. And then position 10. And finally, position 11. Now, since all the characters have been inserted, we have constructed the whole suffix tree. It is exactly the same as the one we constructed before using the first way of construction. How does this new method perform in terms of time and space complexities? The space it requires never exceeds the actual suffix tree, and therefore the space complexity is order n log n. Again, if every position number can be stored in constant space, the complexity would be reduced to order n. On the other hand, the time complexity is actually worse than the first method, because in the nth iteration, we need to insert the $ symbol n times, and each time requires traversing up to n nodes down the tree. And therefore, the total time complexity is order n cubed. In the next module, we will explain how this second suffix tree construction method can be further improved, such that it only requires linear time. Before watching that module, I encourage you to come up with some ideas on your own. If you want some hints, please look at our example again and see how the different insertions in the same iteration are related to each other, and how the insertions related to the same suffix in different iterations are related to each other.